So for today's talk, I'm going to first start with what this paper is actually trying to do. So the definition of the problem, and we're going to look at a little bit of the background. First, I'm going to talk about a little bit of the background in just self-driving cars, some of the vocabulary that's used. Then we're actually going to define what the authors mean by driving style. Then we're going to look at their reinforcement learning approach that they use, a little bit in a high level. And then we're going to go over the results they present with this. And then I will discuss a few issues that I see with this approach. And then I have a few discussion questions that we can finish off with. Okay, so what's the problem? So when you're sitting in an autonomous vehicle, one thing that's really important is that you feel comfortable, right? And the authors say that the only way that people will start to feel comfortable in these self-driving cars is if the car drives like them. So it follows similar driving styles. So for example, you might like to be a little bit safe, drive a little bit further away from every car, drive a little bit slower, so the car should do the exact same thing. The proposed solution to this problem would be for the car to learn how you drive, of course. The way they plan to solve this problem is through this feature-based inverse reinforcement learning to create these trajectories that match the trajectories that you create. Okay, so what the heck is a trajectory? So in the world of autonomous vehicles, we use a trajectory to define a set of points and a velocity that the car will use at each one of those sets of points. So it's basically a path with a velocity. There are several things that have to be assured for a trajectory to be considered good. The first thing is it's feasible. So what does feasible mean? Well, there's a few things that are involved with it, but mainly it's the car dynamics. So how fast can I actually take this corner given the car I have? Then it's the road dynamics and conditions. So is it icy on the road or is it perfectly clear? Then it's safety. So of course there's no collision. The trajectory that I have selected doesn't collide with any other dynamic objects such as cars or pedestrians or static objects such as a light post. Then it's passenger comfort. So what I mean by this is there's no hard braking, so you jerk forward, or significant acceleration, so you jerk backwards. And the final thing is it should obey rules of the road, so lights, stop signs. Then the drivers define driving style as a method of selecting similar trajectories giving driver preferences. So there's a few things that the authors say that driving style should contain. First is the velocity selection. So that's how do you decide what speed you're going to go on any road. Next is the acceleration profile. So this involves how quickly you're going to accelerate. Then is jerk, which is essentially, do you know when you quickly accelerate and you get thrown back in your seat? That's jerk. Or when you quickly brake and you get thrown forward, that's also jerk. Then it's the curvature of the path. So for example, when you're taking a really hard corner and you're pressed against the door, that constraint should be comfortable for you. Then it's lane keeping. Where do you stay within your lane? Collision avoidance with other vehicles, so how far any other vehicle is from you. And then how far do you decide to follow another vehicle? Okay, so to take these, they have to give them mathematical formulations so they can be used as cost functions. So there's a lot of math here, and I'm not going to go over every single one, but it's just important to know that the authors compute each one by taking some velocity and acceleration and position that they recorded from drivers, and then computing all of these properties. So for example, in velocity selection, they take the actual speed of the road, and they compare it to the speed that the driver decided to drive on that road, and that's how they got their velocity selection. And then things like collision avoidance, they calculate the closest car to you. Essentially what they do is they calculate the closest point to any car, and then they consider that as the distance that you chose to keep to every other car. And this will become very important because what the authors plan to do is start to change lanes. So when you start changing lanes, it's very important how close you decide to get to another car. Okay, so what's the algorithm that they're going to use? So before I start, trajectory planning is actually a very hard problem because it can be infinitely big and an infinite number of dimensions. So when you think about it, you can choose anything along an x-y coordinate with any acceleration, with any velocity, and you could decide to get there at any time given the velocity and acceleration profiles you take. So this is a really big problem, and you need a way to quantize it. So the way the authors decided to do that is to take any trajectory and represent it as just a 2D quintic polynomial, and this allows them to basically take these and play with them significantly easier. Okay, then what the authors do is they have a set of observed trajectories that they collected from users. They then calculate all the features that were defined in the slide below. So all of these features are calculated. For every single one of the trajectories collected. Once that's done, they average them, so they make what they call is an average feature vector. So that's basically your average driving style under any conditions. Then they use this to try to take the path that the car creates and move it closer to that average feature vector. And the way they're going to do this is basically by taking their path and then breaking it down into a set of points. And at every single one of these sets of points, they're going to try to optimize 3 variables. They're going to try to optimize the position of this, the velocity that the car is going to take at any one point, and the acceleration. And this happens from time 0 all the way to some predefined time t. Okay, so how are they going to do this? So they first calculate, they generate one of these. And this could be using some other algorithm. Once this generation is done, now they have to optimize. They have to try to get these points closer to that average feature vector. And they do this by basically cycling through this entire thing. So they'll calculate the feature vector for the machine learning trajectory created. Once that's done, they're going to go to each individual point, calculate the gradient, and then using that gradient, they're going to try to minimize the overall cost function. The cost function in this case being the features that we've seen before. That was kind of complicated. So ultimately, they're trying to take the current trajectory that the algorithm is looking at, and they're trying to converge it to some demonstrated trajectory. So here's an example. So let's say that the average feature vector of a car that was recorded by humans is given by this blue line. Okay? So you have to understand that you can't figure this out for every single scenario that the car will be in because you don't know what other vehicles on the road are doing. This is just some average that I'm visualizing just for the demonstration of this example. Next, we're just going to take some current trajectory that's calculated initially, and we're going to try to figure out every single point along here. We're going to try to figure out the features that match to this. So basically, in this case, one major feature is lateral acceleration. So how far do you jerk the car the other way? And you can see that this is significantly more aggressive than the blue line which the user recorded. So then what's going to happen is we're going to try to move closer to that line by gradient descent. The line moves closer, next step, again, until we finally converge to something that the authors call close enough. And this is done after about 30 iterations of this process. Okay, so how did they actually do the data collection? That's very important. So they use some existing set of maps on highways And then what they do is they tell two participants in this case to drive with velocities ranging from 20 meters per second to 30 meters per second. And they tell them to do normal acceleration, normal deceleration, make sure that you drive as you would normally drive with some, okay, accelerate now, change lanes now. All of this data was collected, and then it was separated into lane changing and lane keeping. I am actually not sure why they do this, because at the end of the day, they combine all the data into one average feature vector. They don't actually make a separation for what we call maneuvers, which would lane changing or lane keeping would be a maneuver. And to test this, they tested in a simulator. I can't tell you any more information because they didn't actually provide any more information. They just said, we used a simulator. Then what they did was they told the car, the simulation car, to drive as accordance to one of two users, either user blue or user red, which you can see have different profiles, meaning that one drove a lot more aggressively than the other. One was a lot more conservative. And the authors show, first in this graph, that the actual cost function, so that feature vector that we talked about, the driving style, it obviously got lower as we decreased the gradient. Then what the acceleration curve looks like, so the blue was the one that was recorded. The black was the initial one created by the algorithm, so you can see that it's very aggressive. And then the red is the one that the algorithm finally converged to. So it finally got to this and said, okay, this is good enough. Here's what the trajectory actually looked like in space, so x and y coordinates. So again, black is the initial. You can see it's very laterally intensive. Blue is the recorded, and red is eventually what the algorithm came to. So you can see that it's pretty close. And if you were in this autonomous car, you would feel pretty comfortable. Next, they claimed that this can run on a car because it ran on the simulator, and the simulator was actually able to execute it exactly. So one problem that self-driving cars have is, yeah, you can come up with a trajectory, but if the car that you're using can't follow that trajectory, so if it can't accelerate as fast as you tell it to, or it can't do things like lateral acceleration as fast as you tell it to, those trajectories are useless. So the authors ran this algorithm at 5 hertz, which is 5 times a second, but they didn't provide any specs about the computer that they were using. So for all we know, they could have been using an entire server rack to do this. And this is a problem with self-driving cars because everything has to be done on board the car. And then based on these results, the authors claim, okay, well, this is possibly feasible to be put on a car. Okay, now I have some issues to discuss. So first, there's some major safety concerns, right? If I decide to drive really aggressively on my self-driving car, that affects the entire population, right? What if my driving style is not deemed safe? That's the first thing. The second thing is, because we're trying to demonstrate trajectories, this reinforcement learning algorithm needs to have an infinite number of trajectories to know how to deal with an infinite number of cases. For example, let's say there's a car in front of you and there's nothing you can do to avoid a crash at this point. Let's say it slammed on the brake and now there's nothing you can do. Now this is called an emergency maneuver. So now you have to try to either minimize the accident in some way so that maybe you don't die, or you try to somehow avoid death of both you and the other person. This algorithm can't do that because you can't record user data where you crash into a car. Second, the listed features are insufficient for all cases. So for example, during normal driving, yeah, the set of features that they listed might be sufficient. However, during other maneuvers, such as going through a red light, it might not be enough. Like, for me, another feature that's very important for like regular traffic or at lights is how fast or how quickly do you decide to start decelerating before you get to the light. So some people decide, well, there's 10 meters left, let me slam on the brakes, while others decide 100 meters back, okay, let me ease off the accelerator until I get to the intersection. Next, the set of maneuvers might change depending on the maneuver that you're doing. So what do I mean by the set of features might change by the maneuver? Well, in busy scenarios, such as heavy traffic, of course you're going to be closer to other vehicles. And if the algorithm tries to optimize you being far from other vehicles, you might never reach your goal. You might never actually drive anywhere, because the algorithm is always waiting for there to be less traffic. Second, there's some issues with the results. So 5 hertz from experience is not enough to actually drive a self-driving car. You need to be performing these action maneuvers a lot faster, these trajectory planning maneuvers, so that you can take care of cases that happen really fast. For example, if a kid runs onto the road, you need to be able to react very quickly so that the car can stop in time. Another issue is they didn't actually demonstrate that this can actually be done on a self-driving car, so it was only done, there was only testing on simulation. Only 2 users were selected and only 2 users were demonstrated, which was a bit concerning. And there was no clear numeric response from the users about how comfortable they felt after the experiment, right? They said, oh yeah, the trajectories sort of matched, but only the users that collected that data could tell the algorithm, yes, I felt comfortable with this, or no, I did not. Because humans are very sensitive to even the most minute acceleration or jerk profiles. Okay, so now I have a few discussion points. So first, should we actually allow autonomous vehicles to have different driving styles? One thing that's really good about autonomous vehicles is their consistency, right? We know how they're going to behave in every case. Now all of a sudden, if one is driving super fast and the other one is driving super slow, we run into the same issues that we run in with human drivers. Second, what if the driving style programmed is far too aggressive and it's not safe? Is this okay? What if different users in the car have different driving styles? Whose driving style is going to be picked? For example, I know in my family, my father likes to drive a lot faster than my mother. Whose driving style is going to be chosen for our autonomous vehicle? And I think that's it. That's it.